Hi everyone. Thanks again for attending the webinar. I'm starting to share my screen, so hopefully you can all see it and hear me okay. If you've got any problems hearing me, and just pop a message in the chat and we'll try and help you. We want to focus the majority of the webinar today on really showing you how we can quickly move from some geometry of a part or product and rapidly explore designs and iterate them and validate them. We will also make a recording of this webinar available, so feel free to share that with your colleagues as well. By way of introduction, I'm Rob Shropshire and I lead the sales and marketing side of Origin. I won't be doing a lot of the talking today apart from a brief introduction and hosting the Q&A, but it will be your contact moving forward if you do want to chat to us more after the webinar. I'm really pleased to be joined by Tim, who will be leading the demonstration today, and also does a lot of our training and support for many of our customers. So it'll be a great contact as we approach Q&A to answer those questions. So quite a simple agenda today. I think we're all here for the demo really, but I will start with a quick introduction in terms of what Ansys Discovery is and what some of the challenges are in terms of perhaps adopting simulation earlier, and equally what some of the opportunities are. We'll then get into the demo. Runtime for that is about 35 minutes, so not quite 30 minutes. So hopefully you can forgive us for that, but you will be impressed in terms of how much we're hopefully going to get through and show you in quite a short space of time. I will then save sort of 5 minutes at the end for some questions. So once again, you probably see me post a message in that chat. The chat's public, so yeah, feel free to ask your questions. In terms of us as a company, Origin have around 200 customers. All of them are in the sort of manufacturing design space. We really focus on solutions for designers, and in particular trying to get companies to actually drive their designs through analysis, as opposed to something that's being done towards the end of that design process. And we'll explain why we think that's important on the next couple of slides. As well as providing the software, we also provide the local support and training services here in the UK. The product we'll be showcasing today is from Ansys, and we're really proud to be one of their official partners. In terms of sort of solutions and training time, this always tends to get asked, so we thought we'd cover it here. But Ansys Discovery takes a day to learn, and typically anyone with some sort of knowledge in CAD can pick up the solution quite quickly. So sort of no matter what your company size is, if you've got a bit of CAD knowledge, you should be able to get on pretty well with this product. So as I said earlier, we try to get companies to adopt simulation earlier. I think first and foremost, by giving design engineers simulation tools, we can explore multiple designs, concepts and materials really quickly. We could challenge a design engineer to move towards innovation by providing a safe space to test out ideas, ultimately enabling designers to make the best decisions with analysis. And a lot of the product development costs are spent early on, and the further down the track we go, the more expensive redesigning a part and component is. So we think it makes sense to use these solutions earlier to guide thinking and provide a reasonable level of confidence in our design. We can often validate a lot of early designs through simulations without perhaps having to do a physical prototype or perhaps 3D printing something or doing some physical testing. So we're not suggesting that physical testing is not important in some cases, but simulation can certainly help us to reduce some of those testing costs. We also think that simulation is a great way to communicate ideas with clients and show what is and maybe isn't possible. And if they perhaps give you a brief and you're perhaps producing a proposal for them, and you can quickly say that you've had a look at their geometry, perhaps you've come up with a few ideas and you've proved that you're able to improve the cooling of the electrical components in the design, or perhaps you're able to reduce material usage by X or increase factor of safety by Y. Those types of things I think are going to help differentiate yourself. So lots of opportunities we think, not just in terms of using simulation in the product development process, but actually also in the sales process to differentiate yourselves and hopefully win more work or even add more services. So there are obviously opportunities, but there certainly are challenges. And one of the main ones is looking at the internal resource and that expertise that we've got. So Ansys Discovery has two modes of solving. One of them actually meshes the part for the designer automatically. So it's not a case of having to do sort of any defeaturing of the model, any filling in of the model. It's just a case of putting that geometry in and the software will sort of mesh it for you. So it's a very quick way to get results without a big learning curve. Another challenge may be the total cost of actually buying the software package in itself. Or perhaps you've already got a CAD tool, but would have to buy lots of add-ons to get the types of simulation that you need. Now, there are always limitations with any product you buy, even Ansys Discovery and the one that we're showing today. But I think what you will see is quite a lot of functionality included for a relatively low price point, and probably plenty of functionality in terms of what a designer might need in terms of exploring those designs. Another problem is often the time taken to get analysis results. If it's going to take us days or weeks to get results, we're not going to take the time to wait to get feedback. We're just going to carry on plowing through that design process. Perhaps you typically outsource the more complex simulations or have a team in-house and have to wait for them. So we're not suggesting that you would get rid of any specialist simulation capability because they're important skills to have. What we're saying is there are a lot of routine simulations that designers could do to actually take the burden off those consultants or your team so they can focus on more complex stuff where their experience is really needed. Another thing I hear a lot of is it sounds great, but we need to find the right project to use it on. Or it sounds good, but the customer's not actually asked for it yet, so we don't need to provide it. And in my view, with the price point of Ansys Discovery being what it is for what you get, I'm not convinced you need a customer to pay for it. I think you can just get on using it as a tool to differentiate yourself in the marketplace and essentially add more services. I think it's often hard to sell something that you don't actually own and have. So a lot of our customers that have taken the plunge have certainly managed in time to build more value and sell more services. Okay, so just two more slides from me. The first in terms of what Discovery is. So it's a single license that integrates a CAD package, which combines the ability to import your own geometry from your preferred CAD system, whether that be SolidWorks, CATIA, Inventor, or to create geometry within the system itself. It then combines real-time analysis, including FEA, CFD, thermal analysis, and electromagnetics. So as you're amending and driving your designs, you're getting that live feedback. After the design, it's also possible to use topology optimization to further improve the part and maybe look at things like maximizing stiffness or reducing weight whilst adhering to your manufacturing constraints. Discovery also combines GPU based solvers and CPU based solvers, so users can switch between the software producing the mesh automatically or the user defining the mesh and reviewing the mesh before simulation. So we think it's the first of its kind really that allows both designers and simulation experts to use the software, striking the right balance between accuracy and speed and taking into account where you're at in your product development process. The product's also integrated with other flagship Ansys products like Mechanical or Fluent, which you may already have or maybe your consultants use, so it does integrate in with that. So in terms of the demonstration, we're going to get into that now. We do understand that many of you won't be designing drones. We just thought it would be a relatively interesting model where we can really incorporate lots of those different physics in one sort of demo. So we hope you can apply that to what you're doing. We'll start off with an FEA example to do some basic tests on stress and look at some displacement. We'll then look to optimize that. Once we've done this, we'll then start to look at some topology optimization. We'll then move on to look at airflow and making the design aerodynamic before finally exploring the thermal properties of the internal electronics. So we'll cover a lot of different physics through this session. So with that, hopefully you'll enjoy the demonstration. I'll now be passing over to Tim. We will turn our cameras off now just so that you can sort of see the demonstration properly, and we'll be back on to answer questions. So once again, please do feel free to get your questions in.
Hi everyone, thanks for joining us, and thanks for the introduction, Rob. So I'll be taking you through the discovery software using the optimization of a drone as an example. Hopefully this example shows the power and versatility of Ansys Discovery, and you can see how this can potentially be used on your own products to iterate and improve maybe earlier in the design stage. As Rob mentioned, we'll be going through an FEA structural example. Then we'll be looking at topology optimization. Obviously, we're going to be doing this on the arm of the drone, so just on one particular piece. Optimization in this particular instance might be important. We might be able to improve battery life, maybe maneuverability, that sort of thing. We'll then look at the external fluid dynamics of the drone with initially an unoptimized part, and then we'll look at obviously a more aerodynamic part. And we'll also show off potentially a few of the modeling features within Ansys Discovery and how you can quickly create shapes to explore new concepts. Finally, we'll look at the internal thermal characteristics of the drone to ensure that it doesn't overheat during use. So I'm going to jump into an FEA example, and we're going to be running some structural optimization on the frame or the skeleton of the drone. I'm not going to delve too much into the UI of Discovery, but in short, it's a powerful modeling and simulation tool. We can import all data sets so it can work alongside your existing CAD tools. It also plugs in to Ansys flagship products such as Mechanical and Fluent. The first thing I'm going to start to do is I'm going to change my material type. Whenever you import a part into Discovery, it defaults to structural steel. You can change that if you want. But you can see here, this is our material type. This is our assembly tree, and then we've got our physics tree underneath. So I'm going to double click that, and we can see our library of preset materials. We can get access to larger material libraries through Granta Materials. And you can also create your own custom materials within Discovery as well. So I'm going to change this to a plastic. It's going to be more of a recreational drone. So this is a plastic, let's say ABS high impact. So I've changed the material. That's the first thing, and we can see that change appear now in my physics tree. Just another thing to note is I'm going to be running my simulations in the GPU powered explore mode. So we can see we're in the explore mode at the moment. We do have a refine mode, so this will allow us to actually mesh the part in maybe more detail. But I'm going to be running most of these in the GPU mode, just to allow me to get through all the simulations we wish to show, and also allow me to get that quick feedback on any design changes I make and see if those design changes make my part better or worse. So the first thing I'm going to do is I'm going to set up the forces on the part. So we have our sort of drone arms, and this is where the motors, the propellers are going to sit. So that's where a lot of the weight is going to be on the drone. So I'm going to go into my structural drop down in the simulation tab, and I'm going to apply some forces. So I'm going to apply a force of 10 newtons. This is probably over exaggerated in the amount these parts might weigh, but we do know obviously with acceleration things do get heavier as such, but so we want to sort of maybe increase that ever so slightly. So I'm going to put 10 newtons on each of these bases. So I'm going to apply 10 Newton force. As I'm doing this, you'll see the physics tree start to get populated in the left-hand side. So now we can see the forces that I've applied. We also can now see our contacts. By default, it presumes that all these are bonded contacts. I'm going to leave that for the moment, but I will show you how you can change those later on in a few minutes. The next thing I need to do to actually be able to get some results in my simulation is to add some supports or add a support somewhere. So what I'm going to do is I'm going to just apply some supports to maybe these faces. I'm just going to hold control and select all these faces here. We can use this little quick HUD access guide to select the same tools as in the tabs, and I can see the supports all there. I can show what type of support it is. Let's say it's fixed. and I'm going to hit the tick box. As soon as I've done that, my setup is okay. We can see that gravity isn't included. We can include gravity, but the solve button becomes available. So as soon as I hit this solve button, within a few seconds, I'm going to get results because it's using, as I say, the GPU powered simulation. So if we look here, it's just solving at the moment, but you can now see this is completely green. If we hover over it, it will say complete. I'm looking at displacement at the moment. I'm going to change my units to millimeters, and we can see the displacement that this part has. We can animate it. This is over exaggerated, but we can do true deformation as well, so we can see that there. So that's our displacement. If we look up here to the top here, we can see our factor of safety, obviously max displacement. See, these are just the default monitors that get put in. We can create any monitors we want on any part of the model we wish. So these are all just custom ones, and we can see all the different types of monitors that we can add. I'm going to look at stress. So let's have a look at von Mises. Obviously, we can see that our part is potentially safe. We've got a factor of safety of nearly 12, but we might be able to make improvements to that just by making small changes to the model. So we can see our max stress on the part is 2.4 megapascals. I can over exaggerate the areas very easily, so I can start to see potentially where the higher areas of stress on the model are. So I can see potentially it's these top areas. We're also getting a bit of high areas of stress maybe in these corners. So let's make some model changes. If I go into the design tab, one of our 4 main modeling tools is the pull tool. So if I select on these edges, at the moment they're just sharp edges. We all know generally rounded edges will hopefully be slightly better. So I'm just holding control, going through and selecting on these edges. Forget the edge, not the point. Okay, so I've got all the edges selected. I can manually start to add a radius, and you can hopefully start to see this, but I can also actually type in a value. Let's say I want 15 mil. So I'm just going to hit enter, type in 15 mil, and what will happen is the solution will re-simulate, and within a few seconds we'll get some results. I'll hopefully see whether I've improved the model or made it worse. So if I look at my factor of safety, we can see that we've gone from, I think it was 11.3 to 11.6, 11.5. So it's slightly improved by adding those radiuses, which I'm happy about. But we can see again the high areas of stress are maybe on this top face here. So maybe let's see what happens if I actually just thicken this face by a little bit. So I'm going to use my move tool now, and just use my move tool to extrude this top face ever so slightly. Let's just type in 2.5, and we're just thickening that face by a few mil. Let's see what effect that has on my factor of safety again. So again, I've gone from 11.4 to 11.8. So not huge changes, but definitely improvements in the model. So you can see the direct effect of the changes you make on the model and what they will have. I just want to quickly show another couple of things in terms of FEA. Obviously contacts is a big one, so I'm just going to hide my results for the time being. Just get back to the model, and we can see here obviously our contacts, they're all presumed to be bonded at the moment. In reality they're probably not, so I can start to change them if I wish. So if I look at the contacts maybe just between this arm, so there's all the contacts at the moment between this arm are just presumed to be bonded. I might want them all to be let's say sliding, for example. So because it looks like obviously we've got some bolt holes that maybe will hold this part together, so I'm just going to convert those to sliding. We'll do all the same to these, and we can go through them very quickly and just convert these to sliding. You can also see that we can use idealized or frictional, but I'm going to just use idealized for the time being. So now we can see that the bonded contacts, I'm just left with this sort of plate on here, which I'm okay with that. Then if I wish, I can start to apply different conditions. So in my simulation tab, I could then potentially use the joint tool. I might apply joints between this part and this and start applying joints. So we can go through and actually apply different conditions as such. Another thing that we can do in terms of FEA is we can also use our bolts tool. So if I click the assign tool here, I can pick a hole, select the similar size bolts, and then I can create bolts through these holes. Once those bolts have been created, we can also add a bolt preload to these. So if I click on any one of these bolts, because of the same bolts, we can add this, automatically add the same preload to all of them. So we can add a clamping force, a torque, and that sort of thing as well. So so that's just something that we can do with Discovery as well in terms of FEA. That was just a quick example showing FEA on the skeleton of the drone, making a few little design changes and seeing what effect they actually have on my results, whether it makes them worse or better. So now we're going to move on to a topology optimization example to see if we can achieve some weight savings on a component in this example. I'm going to use the drone arm as the thing that I'm trying to optimize. And obviously there's 4 of them, so if we can maybe achieve some weight savings or improve performance, then that probably could be a good thing. One thing to note is when doing topology optimization is it doesn't always have to be about weight savings. You might be actually looking to improve the stiffness of your parts or something, or other objectives or target frequency and stuff. So it doesn't always have to be about minimizing mass. Potentially you might be looking to increase stiffness and other objectives. So the first thing I'm going to do is I'm going to create a new simulation. So here we can choose, we can set up a new simulation. So this is just a new physics simulation here. So you can see that we can jump back to the old one, but now we're in a new one. Obviously you can rename them and that sort of thing. And then I'm going to use my quick scope tool just to change all this to none, and then just choose the one piece I'm actually looking to simulate on, which is this. So that's now the only thing that's included in the simulation is this one arm piece. So then I'm just going to right click and hide all the others. So that just separates everything so I can focus on that one piece. So the first thing I'm going to change, as it's a new simulation, it's defaulted back to structural steel. So we can click this and we can change that to ABS again, high impact, which is what it was. So we've done that. And then the next step is just to set up a structural simulation exactly like we did in the previous example. So first thing to do is choose some supports. In this example, I'm just going to just choose these 4 areas as fixed supports. And then I'm going to add my force to this face here. And I use the same value that I did previously, so I'm going to put 10 newtons. So that's my structural simulation set up. One thing I'm going to do here is actually put a new monitor. I'm going to make that a custom monitor, and I want the actual mass of this part. So I'm going to hit the tick box there. So we can now see that we've got this mass monitor, just so I understand maybe how much this weighs to start with. So if I click the solve button, in a few seconds we're in the explore mode, so we're going to get some results. So we can see pretty quickly our results. We can see this part weighs around, let's say, 200 grams. So that's how much the part weighs. Now we can start to set up our topology optimization. So to do that, we just basically turn it on up here. And this will add our optimization targets. I'll come back to these in a second. If we look in our tree, we can see the optimization has been added to our physics tree. I'll go through these targets in a second, but you can also see we've got protected depth. I might be looking at that and actually saying, actually, that's too much. I don't really want it to be that protected. So if I double click this area, I can obviously change this. Let's just change that, and we can see that we've just changed the protected depth. Any face or any area on the model you can protect. So let's actually want to maybe protect this area more. I can increase just that area, and now you can see this area is protected by that much, and we've still got the smaller amount in this area. So that's just something with the predicted depth. I'm going to just change that back to what it was before. Now looking at the optimization targets. So if I double click here, we can see that we've got our objectives first of all. So we can maximize stiffness, target frequency, minimize stress, minimize volume based on stress. So just to go through a couple of these, obviously I am going to use maximize stiffness, but another nice feature within Discovery is the minimize volume option. And here you can actually target a maximum stress. So if you want to make sure that it doesn't go below that stress value, you can target that. In the latest release, which is coming out hopefully this week, you can also target a factor of safety. So if you want to get to a factor of safety of 8 or whatever, you can do that as well. I'm going to take that to maximize stiffness. Hopefully you can see here we've just got a volume reduction target which you can set. And then you do also have manufacturing constraints. So depending on whether your part might be molded, 3D printed, machined, you can set your manufacturing constraints if you wish. So I'm just going to leave those without any manufacturing constraints for the purpose of this. And that's I'm happy with my volume reduction. So that's my setup sort of complete. Just another note, you can do multiple load cases as well. So you can have multiple load cases if you want to study those as well. And now we've done that, we can hit the solve button. As we start to solve this, we'll start to see material being sort of chipped away. So in a second, we'll start to see the shape of the part start to change, and material will start to be, as I said, sort of chipped away. And we'll see that in a second. For the purpose of time, I won't let this finish all the way, but we can start to see how the shape is changing. Once you're happy with the shape, obviously, once it will finish eventually once it's reached your target reduction. But if you're happy with the shape at any point, you can always pause the simulation, and then to get your optimized shape, you basically use this option here, and that just adds the optimized body to the model. So you can see now this is our optimized shape. It is in a faceted format, so you can see it's a faceted model at the moment. There's a couple of things that we can now do, which is quite neat. We can right click and we can create a validation simulation. So we obviously want to make sure this part, we want to validate this part. So we can do that using this option here. We can also, if I just quickly do that now. So this basically applies your structural simulation to the faceted body, and then obviously we can simulate on this, and then we can check our results and check the new mass, check the new factor of safety and other things. So we can see factor of safety 15, obviously lower mass. So we've improved our part without having a drastic effect actually on the factor of safety, which is good. We can obviously then look at displacement and other things. So that's creating a validation solution, and that's actually doing it on the STL model, which is quite a nice feature. Another thing that we can do is if we right click on here, we do have the option to also smooth the facets, and we also have the option to reverse engineer this. So we can actually convert this to a solid basically. In order to convert this to a solid, we might want to first smooth the facets. This will just basically create us a new STL, a new faceted model, but it's obviously going to be smoother, which we'll see in a second. And then once we've done that, we can actually then go on and reverse engineer it with sort of one-click reverse engineering. So once we've done that, we can right-click on here, convert to solid. I'm going to say using surfaces, and then this will convert this to a solid geometry, which could be saved out as a parasolid, a step file, rather than an STL or an OBJ in faceted format. So we'll see that in a second, the final result. So you can either export this out as an STL and potentially reverse engineer over it yourself, or you can let the software convert this back to a solid. Once this is complete, you'll end up with something that resembles this. So it is a patch surface model, but this can be exported as a step, a parasolid, any solid format you want. It is a solid body. So you'll end up with something like this that can be exported. So now we're going to move on to external fluid flow. So the external fluid flow is going to be run on the external part of the drone. We're first going to look at an aerodynamic part, and then we're going to look at more of an optimized aerodynamic shape. So I'm going to open up the original drone that we first looked at a few minutes ago. So to study the external aerodynamics of our drone, we'll begin by looking at an unaerodynamic part, and then show how this can evolve into a more aerodynamic part, showing off a couple of Discovery modeling functions along the way. To simplify things, we'll just be simulating on the outer shell of our drone. So I'm just going to open up the outer shell of maybe our unaerodynamic, our starting point, which will look something like this. So we can clearly see very simple design, very unaerodynamic, no rounded corners, nothing like that. So as I say, in this example, we'll just be studying external flow. We also can study internal flow with the Discovery. So these are a couple of the features within our internal flow. We can do porous media, rotating fluid zones. We can also do intake and exhaust fans. So if that's more of your thing, you're more internal, feel free to drop us a message after the webinar, and we're happy to give you a more personalised demo of internal fluid flow within Discovery. So very easy to set this up within Discovery. We can use our quick start guide. We're going to be doing an external flow. We can choose our direction. So I'm going to say that's the front. And then we can choose a ground plane. We can modify this as well in a second. So this basically almost creates as like a sort of a wind tunnel thing, which we can resize. This is just a default size. We can resize this. I might want to actually make this a bit smaller. So I can use some of my modeling functions. In this instance, we're using our pull tool, which is like an extrude tool, just to change a couple of things. Let's make the height a bit smaller. So you can see, I'm just eyeballing this, but you can see this this fluid zone can be modified, and you can create whatever size you wish. Once you're happy with the size, let's just make it a bit smaller there. We can look at our physics setup, which we can see is already set up. We can see our material. Again, we can change this if we wish. Let's change that to the material that we're using before, ABS, and we can change the fluid from water to, let's say, air, which is more realistic. Here we can also turn on gravity, include buoyancy, so we can turn on gravity. I'm going to just not include that for the time being. And if we look at our inlet, we can see the speed at the moment is 0.25 meters per second. We can change this here, and I might set this to miles per hour. Let's say the drone's going to be traveling at 40 miles an hour. So that's our setup complete. We can now click our solve tool. Within a few seconds, we're going to start to see some results appear. Once this is complete, which it is now, we'll see our results. So at the moment, we're just looking at vector velocities. We are looking at velocity, and we are looking at vector velocities. We can show an animation of these, and we can change all our simulation things like thickness, tail length, count, search, just looking for certain magnitudes. We can search for different areas. So that can all be customized to suit. We can change our views to ISO contours, particles, and also direction field. So I like to look at, when I'm doing external flow, I like to look at the direction field. So obviously one thing we can see straight away is we can see quite a large separation region. Obviously once this fluid sort of hitting the front of our part. If we look here, we can also see some sort of turbulent flow down here as well. This direction field can also all be moved. We can study different areas, so we can study different areas, as you can see here. So that can be moved along our part, and we can study different areas. So we're just looking at velocity there. Other things we can look at, we can start to look at pressure and static pressures and other things. When you're looking at pressures, you might want to look at the ISO surface and that sort of thing as well. So that's our pressures. So that's just a quick look at external aerodynamics of our drone. Won't go into too much detail, but what I'm going to do now is show you a couple of features of our modeling. So I'm going to go into our model mode and show how maybe we can use some of Discovery's modeling tools to create a more aerodynamic part. So what I'm going to do first, I'm going to create a sort of a work plane, and I'm going to just create another work plane. Let's just create one in the middle as well. So I'm going to select those two faces and just correct. So I've just created one work plane here, one work plane there. From this, I'm going to just start sketching a new profile. So I'm going to right click here and say new component, just so I'm working on a new component. This will be my more aerodynamic shape. I'm going to go into a sketch mode and just draw a shape. I'm just going to draw a rectangle, and let's say let's start with maybe something that looks like this. I'm going to use my create rounded corner tool, and I'm just going to round these corners off. So let's go from here, and we can create whatever rad we want. Let's go 20. And you can see I'm eyeballing a lot of this, but you can create whatever geometry you wish. So you can see I'm just going to do that on both sides. So we can see the shape that I've created. I'm going to go into a 3D mode, and that will create me a surface. If I hide my original drone, you can see a surface being created. I'm going to create one more surface, and basically I'm taking sort of inspiration from sort of maybe a plane wing. Maybe we're looking at like a sort of a teardrop shape. So I want to be able to see this one. I'm going to make this one ever so slightly bigger. And to do that, I'll just project this onto my sketch grid, and I'll just use my offset curve tool just to offset these by, I don't know, 10 mil, let's say. So that's my neck shape. Delete these two here. And then I'm going to just use my move tool just to move this one maybe to the back. And I'll make this, using my pull tool, I'll make this just ever so slightly smaller. So I'm just doing some basic modeling here. So that might be the profile of my new drone. I'm going to use then a blend tool, so a loft tool, just to sort of create a profile between these. So this is my new profile. That's a little blend. Then let's finish it off by adding some rounded corners. So I can use my pull tool within here to create some rounded corners. And you can see that here. So so you can see very quickly we can probably create a shape that might be more aerodynamic than previously. So that's just showing off a couple of the modeling tools. But what I'll do is I'll open up the sort of finished model, which is our more aerodynamic shape, and let's just run a quick simulation on that just to show the results on a more potentially aerodynamic shape of our drone skeleton. So exactly the same setup. We go into external flow, choose our inlet, choose our ground plane. As I did previously, you can modify this fluid zone. You can go a bit smaller. Let's just make that ground plane off the body. And change our setup again. So let's just change that to ABS. And our water to air. Change our inlet speed lastly to 40 miles an hour, same as before. And you can always create your own fluid volume as well and do this manually without the quick start guide. But very quickly, within a few seconds, we'll start to get more results on a more aerodynamic part. So now that's complete, we can start to look at our direction field, and straight away I can see probably a smaller separation region for sure. Again, maybe less turbulent flow as well around the exit area as well. So you know, you can straight away see an improvement from going from one design to another. So that's all the evolution as the design goes along. We can simulate as we go and see those improvements, and obviously we can also validate them with the actual results themselves. So that's just a quick example of external fluid flow on our drone. We're going to finish this off with just some thermal simulation on potentially the internal electronics of our parts and seeing what thermal properties they produce. So I'm aware that I'm running a little bit over on time, so this will be a very quick thermal example. So I'm going to just run this thermal example on the propeller sort of component, the motor within the propeller of the drone, just to give us an idea of thermal properties. And I'm also then going to show a parameter study. So this is something else we can do in Discovery to allow us to study multiple things, multiple simulations very, very quickly and understand the results. So first of all, let me just open up a model. It's just going to be, as I mentioned, just going to run this on the motor within the propeller of the drone. So we can go through the setup again. We can change our material properties and stuff. So if material properties do need to be changed, let's change this to ABS to start, and then we can just change some other material properties if needed. For example, if we have got different materials in the model, we can change these as we wish. So I'm just going to just change these just to a few different materials, just so you can see this, and I'll change that to maybe a copper. So I've just so you can see now in my setup on the left hand side, I've just got a few different materials. I've got the plastic, I've got aluminium, I've got copper. So this is made up of a number of different materials. Let's say. What I'm going to do now is just add a simple thermal property. So if I go into my solid thermal, we can see we can add temperatures, we can add convection rates, we can add heat source, and we can add insulated faces. So if I click on heat, I'm just going to apply a heat to this face here, and I'm going to just type in a heat of 1 watt. So straight away, I can get some results, and I might want to know what the max temperature of areas are and maybe the different temperatures around the area. So if I hit the solve button, within a few seconds, I'm going to get some results. So we'll start to see those, and we can see areas and how that differs. So we can see we hit a max temperature of 42 degrees here. We can see the temperature variations within the parts. We can section our model if we need to and get inside and pull calculations off like we've seen in other simulations. But one thing that's quite nice with the Discovery, another cool feature of Discovery, is the ability to run parameter studies. This works in fluid structures as well. To do that, for example, in this instance, I might want to study how this motor heats up as maybe as we go, the drone goes faster as it speeds up as we're producing more power through the propellers. So if I click here and add this as a parameter, I can click here. This is now a parameter. And you can add multiple parameters. So we're just studying one here, but you can have geometry parameters, you can have physics parameters, you can mix and match as well. So I can select the parameter, which is this one, and I might want to know the temperature, the max temperature as my drone speeds up. It goes faster between 1 watt and say 10 watts, for example. The number of variations in between, I might want to study 5, but obviously you can study as many as you want. So I can create those defined variations now, and then I can click here, I can click update all, and within a second or a few seconds in this instance, we'll end up with our values, our maximum temperature values for each of these different power outputs. So very quickly, so we can see just studied 4 things. Within a few seconds, we've got all our different results. Then you can always jump to a different one, different version that you want. You can jump to that setup. But that's just another thing that we can study with parameters. I was going to do a little bit more of an in-depth thermal simulation and just showing the internal of the drone with maybe some intake fan conditions, and also it would have been a CHT. So something to note with Discoveries, we can also do multi-physics. So we can do things like fluid thermal, CHT, fluid solid thermal, and things like that. So we've only done singular physics in this drone example, but do note that we can do more. So that's going to be the finish off. So sorry I couldn't do more on the thermal side, but hopefully this demonstration has given you a bit of an understanding of the power of Ansys Discovery and the physics available within it. There are obviously a lot of other things that Discovery is capable of that we just don't have the time to show in sort of a 30 or so minute demonstration. So if you do have questions, feel free to put them in the chat. Feel free to reach out to us after the webinar, and we're happy to give you more in-depth overviews and demos in terms of what you are more focused on. Keep an eye out on our YouTube channel because we will have a CHT of the internal of this drone, on a little video going out on that in the next week or so. But I'll now pass you back to Rob to sort of close the demo, and we'll answer any questions that anyone's had.
Thanks, Tim. I'll just start sharing one more slide, just in terms of my details. If they flash up, I think I've had a few problems of internet, but I'll try and get them up in a minute. But you will get a recording of this, and we'll be in touch to follow up in terms of what you thought about the webinar. So we'll be there to answer any questions. We have had a couple that have come in. We've still got 10 or so minutes left, so I think we've probably got a couple minutes worth of questions here. So feel free to put some in, or otherwise we'll give you a bit of time back once we've answered these. So to start with, I'll take the easy one, Tim. You can take the more detailed ones. So the first question, obviously we haven't really alluded too much to the both modes. Obviously you've been using that explore mode, I guess, to get the fast results and show how we can, how we can sort of model and get results live. But someone has asked about, the refine mode. Just clarify that in terms of what it is and what it means, and also there's a question, how do you know which mode you need? So if you could just cover that, would be great.
Yep. So generally, what I've just shown there was the explore mode. The explore mode is great for quick model exploration. The refine mode, generally the way you know which model, what you need, is down to the size of your model. So in the explore mode, it's doing like a voxel based mesh approach, which is great. But if you do have a large volume part with very small wall features, that they can be, sometimes maybe it won't be picked up. So if that was the case, we'd probably recommend the refine mode. Also, just sometimes you might use the refine mode to validate. Maybe you do want to actually define your mesh and say, I want local mesh settings in certain areas of interest, and different size meshing and that sort of stuff, which you can do in the refine mode. So it's more of a traditional approach to meshing, really. In the explore mode, it is using this voxel-based approach, which does allow you to get quick results because it is using the graphics processor. So it really depends on a number of things, but a lot of time, model size and what your particular model is. Should I take the next one?
Thanks. Yeah, I mean, there's a quick one here. How long's the free trial? So that's an easy one. It's 30 days. If you want a trial, reach out. whether it's just you or the whole team, we don't mind sticking the technology into the whole design team to test it. We'll support you on that, so we can look at a model, we can provide an initial demo, show you how to set things up, and then let you loose on that one. So nice and easy one there. There's another one, obviously, really, I think getting at the fact that you've got a CAD tool already. And I think, there's always a question, why should we use something like this? I think inherently CAD tools have done a great job over the years of developing some pretty decent FEA stuff, which comes as part of the package. We would suggest that Discovery does have quite a nice user interface. We'd say it's very quick, it's very easy to use. Perhaps it's not locking up a CAD license, so if you're needing to do actual CAD work, but you're using that same license for simulation, often you can't use it. But I think the main reason that, the main power of Discovery is the multiple different levels of physics that you've got. So if you are wanting to combine actually FEA with looking at some topology optimization and some weight savings, whilst adhering to those manufacturing constraints, perhaps you're looking to review, fluid or thermal properties, then it is all part of that one single license. So we have had many customers that have a CAD tool, it's got some FEA in with that, but as soon as they start jumping up the levels and going for more complex physics, it quickly becomes really expensive. So we'd say that's where Discovery plays really well. The final one, which I've saved for you, Tim, it's maybe you can see it, I'll read it out anyway. In terms of heat, what about heat transfer coefficients at surface air boundaries, characterization of flow affecting HTCs and HTCs between various bodies? So quite a lengthy one, that, but hopefully you can answer that.
Yeah, hopefully I can try and answer that. As that, again, if I'm misunderstanding you, feel free to reach out after the webinar. But basically, when in this example that we just shown, we were just doing a pure thermal example, which the outside phases would have a convection rate. So that's how you can modify that depending on potentially what like mode or where you are. If you are doing maybe CHT analysis where you do have like a fluid body touching a solid body, then you can define those as well. And obviously the actual heat transfer coefficient values and stuff, that'll all be in the material properties of the parts. So that'll all be defined in the actual settings of your material file. And obviously you can create your own and that sort of stuff. So I might have answered that, but if not, hopefully you can reach out after the trial. And there is one more one about the stability of the software. Do you want me to quickly touch it? I mean, really, we like to think the stability is, again, hopefully I'm understanding you, but I'll just presume stability, a lot of it will depend on obviously PC power. If you've got a really good PC, obviously the software is going to be more stable. But I mean, the software we like to think is very stable anyway. As long as you've got the minimum requirements, you're pretty good to go. As we mentioned, there's two modes: Explore and Refine. The Explore mode does require a graphics card, and it does require an NVIDIA graphics card. And generally, we say the better the graphics card, the quicker you're going to get results, and maybe the lower fidelity you might be able to get to. Ross is just so touched on that. Another question just come in terms of minimum hardware requirements. Minimum hardware requirements are one, an NVIDIA graphics card, and then two, a minimum of 4 gigabytes of video RAM. So those are your two requirements basically for the GPU mode.
Yeah, and I think we've, through the trial, stability is an interesting question. Obviously, we're going to say it's stable, but that's the purpose of the trial, both to check you've got the correct hardware in place and both to have a play around and make sure it's stable. But yeah, we're pretty confident you'll find it relatively stable, hopefully. I'm having trouble sharing my contact details on, just in case you do need to contact us. But as I said, don't worry, we'll make sure you get an email out. We've got your email when you registered, so we'll make sure we get all of our contact details to you. There's still 5 minutes left. I don't want to keep you here for any longer than we need to. If anyone has got any last minute questions, then put them in now within the next sort of half a minute or so. Otherwise, we'd just like to thank you for your time. Hopefully what you've seen is a relatively easy tool. We've quite a bit included in with it. Thanks, Ross. Does Discovery deal with plastic material behaviors? Tim, another one for you.
So by that, I presume again, obviously we can do plastics, but by that I presume you mean a lot of plasticity, like linear and non-linear. At the moment, we only do linear in terms of FEA. Non-linear, it is coming, but it'll probably be in future releases.
Okay, great. So I think we'll leave it there. Yeah, it's worth saying if there is something we haven't covered, you know, there are other Ansys products, and as I've said, you know, these products do integrate in with that. So usually we've got an answer for everything. It's just a case of deciding which package you're in. But hopefully you've enjoyed what you've seen today. Yeah, we'll get the recording sent across to you and follow up with you just to see if you need anything else from us. So once again, thanks very much for your time, and have a great day.
Thanks, guys.